class.
That's not for learning.
Time for learning is over. Okay, anybody have any homework questions you want me to go over?
I should start doing it.
No, I don't think so. Only if you're a little behind. Okay, so now we are done with the second law. And we're going into the Rankine power cycle. And there are two reasons we're doing this. The first one is we're going to do this as, so it's one example of an internally reversible power cycle. And it's simple enough that we can use it to derive some of the equations that I just kind of gave you cold when we were talking about the Kelvin-Planck statement of the second law. So we can derive some things like, let's say we can derive some things we've seen before, like what we're going to do today is we'll derive the ideal efficiency. Okay, so like before I said, okay, the efficiency of a power cycle is 1 over QC over QH. And then I said the ideal efficiency of a power cycle is 1 over TC, 1 minus TC over TH, right? But I didn't say that seems like a big jump. Like, how can we assume that? Well, today we can use this to show why that is. So that's one thing we can do. Second, this is actually a simplification of a real way that power plants work. So not, there are infinitely many internally reversible power cycles. They all have the same performance if you assume, perfect efficiency. But this version of an internally reversible power cycle is actually used. And so this is also sort of practical information about stuff that's out there. Obviously, the ones that are actually used aren't really internally reversible, but this is just a simplification. And we'll talk about corrections as we go for reversibilities, irreversibilities. So this is used in coal, oil, solar, like lots of different types of power plants, nuclear, and biomass power plants. I always picture biomass as like people shoving like whale carcasses in the furnace, but I think it's actually grass.
I think it's because of the
Okay, so here's how this thing works. You have a boiler. So all power plants work by having some furnace or whatever, that the boiler that heats things up. And then from there, it goes to a turbine. I'm going to always use this as a turbine thing. And so work from the turbine comes out there. At the boiler, heat comes into our system from, the furnace. Then it goes to a condenser. We know that even in the ideal case, you can't have a power cycle where all of the heat energy is used as work. You need heat to be sent out in the exhaust. So this is called the condenser. Because the gas in the system is condensed into a liquid in this stage. And this is where heat leaves. So I'll call that QC. And then we go to, okay, so now we get to this problem. Here's where, so far, if you have perfect efficiency, you could have like a perpetual motion machine, but now we need some way to get from the low pressure and low temperature condenser to the high pressure, high temperature boiler. And so there's no way to avoid having a pump of some kind. And that means that work has to be done on the system. You need electricity or potentially mechanical power in order to power that pump. And the names of these stages, so we're going to think about this. Each one of these processes goes from one state to another, and we're just going to name the states between these processes. So this is state 1. So state 1 to state 2, it goes through the turbine. State 2 to state 3 goes through the condenser. State 3 to state 4 goes through the pump. Okay, so this is called the ideal Rankine cycle. We'll see that people make modifications to these to make things more efficient in practice. But this is the first one we'll think about. And so here are what these processes are. So for the ideal Rankine cycle, from state 1 to state 2, this is an isentropic turbine. Who remembers what isentropic requires? 2 things. It does mean constant entropy. And then, yeah, what are the, so it's hard to visualize entropy, but what things that we can, well, this is a turbine, so there's definitely work. It requires no heat transfer and internally reversible. Of course, we're assuming internally reversible. I've already said that like 5 times. So the question is, this just has to be insulated or no heat transfer. And I'm sorry to make you erase, but let's call this isentropic expansion through the turbine. And the result of this is where you get power out of the power cycle. So you generate power, WT, T for turbine. And all of the arrows show the directions that we're going to call positive. Okay, so QH is coming into the system, QC is leaving the system, WT is going out. WP, this is the first time we've ever, in talking about the power cycle, this is the first time we've ever thought about needing a pump. But this WP is going into the system. And so the total power that you get out of this thing, you can think of as, later we'll talk about this. We're getting the power WT minus the power that we have to put back into it WP. So really what we're getting out is WT minus WP. From state 2 to state 3, we have an isobaric, so constant pressure, heat rejection to the condenser, if you have room here for this first stage going from state 1 to state 2, since this is isentropic, what this means is that the specific entropy at state 1 is equal to the specific entropy at state 2. So these are the things that we're going to use when we start doing these calculations. Okay. The isobaric heat rejection, that means that since it's isobaric, the pressure at state 2 is equal to the pressure at state 3. Then from state 3 to state 4, we have another isentropic process. So this is an isentropic pump to get the liquid to a higher pressure. And so we know that specific entropy at state 3 is equal to specific entropy at state 4. And then finally, to finish the cycle, we go from state 4 to state 1, and this is another isobaric process where heat is added at the boiler. And so the pressure at state 4 is equal to the pressure at state 1. And one thing that's going to be really useful to us in thinking through all this is a temperature entropy diagram. So we'll have temperature on the vertical axis, specific entropy on the horizontal axis. So people just call this a TS diagram. And in the TS diagram, you can see the vapor dome really clearly. And this is state 1. So from state 1 to state 2, this is the turbine. What's happening to the temperature and the entropy?
Temperature is going to go straight down, right?
Temperature goes, yes, so it's going to go straight down, exactly. The temperature is going to go down, and we know that it has to be straight down because it's isentropic. There's no change in entropy. So we're going to go straight down to here. And this is state 2. At state 1 and state 2, what can we say about the phase of the material?
Stays the same, doesn't it? No.
Well, you can look at the vapor dome and see. So if you're on the right side of the vapor dome, what do you know about the phase that you're in? It's not, if it's on the line, it's saturated, but it's not a mix. So this is a saturated vapor at state 1.
And then it goes to a mix.
And then it goes to a mix, correct? Any questions about that? Now, through the condenser, since it's a mix, if you take energy out, you're just going to get, so here's what you know, is if you keep the pressure constant for a mix of vapor and liquid, and you take energy out of it, the temperature stays the same while you just go to a lower quality, okay? And so the next process goes all the way to a saturated liquid. And so state 3 is a saturated liquid. Then we're at the pump. That's isentropic again. And so that just has to go to a slightly higher temperature. And from there, we just follow a constant pressure process of adding energy. So it's going to go up to here and then over to here. So it's a compressed, liquid at state 4 because it's to the left of the vapor dome. And then energy goes into it until it becomes a saturated liquid. And once it's a saturated liquid at a constant pressure, as you keep adding energy, the temperature stays constant while it turns into a saturated vapor and gets ready to go through the cycle again. Okay, so this is a TS diagram of the ideal Rankine cycle. And remember that from this diagram, you can always tell, so from the TS diagram, you can always tell the phase. And you can always see the isentropic processes. It turns out there's ways to make this a little more efficient, so we'll talk about those later. So later, we'll discuss 2 improvements to this cycle. 2 improvements in practice. To this ideal Rankine cycle. The first one is called superheat. And so if that's the vapor dome, in superheat, you go from state 1 to another superheater, and bring that vapor, instead of going straight through the turbine from here, you put more heat energy into it to make it a superheated vapor. Then you go down from there to the through the turbine. Then through the condenser, the pump. Okay, so this part here is the superheater. And the other improvement we're going to talk about is reheat. So the way the reheat works is you go through the superheater, then you go through one turbine, then you reheat and go through another turbine, before going through the condenser and then through the boiler. So these two are 2 turbine stages. Okay. So now we're going to see the benefit of having an actual power cycle that we've decided on. So for doing calculations about, whatever. What we're going to do here is, so now we'll use the ideal Rankine cycle to show that the efficiency for an internally reversible power cycle is 1 over the temperature at the condenser divided by the temperature at the boiler. And what's the point of that? Well, since all internally reversible power cycles using the same reservoirs have the same efficiency, this is, what we're calculating then is the ideal efficiency. So before I just gave you that, believe me, this is the ideal efficiency, but now we can check it for this thing that has these 4 stages where we can actually do calculations. Okay, so here's the proof. So since this is internally reversible, we know that the change in extensive entropy is given by the integral of delta Q over T. And we can rewrite this in like a differential form as an infinitesimal increment of entropy is equal to an infinitesimal increment of heat transfer divided by the temperature. And this d capital S we can write as, as m d little s. And then, move stuff around and you get that TDS is equal to m delta Q. No, that is terrible algebra. This is dq over mu dq. And so now, if we integrate both sides, we get TDS integral is equal to the integral of delta Q over m, which is equal to Q over m. And we're going to assume this is steady state, which means we can think of this as Q dot over m dot. And now, I forget what law of calculus this is, but there is some temperature in this range of temperatures that we're dealing with where we can write this. So we can rewrite this as some T bar times the integral of ds is equal to Q dot over m dot. Okay, so this T bar is for some temperature at the boundary. Okay, during that process. And so now we can come up with this final result that says for whatever temperature that is, some temperature at the boundary, which we can think of. So if we're talking about like the boiler or the condenser, this is just some temperature at the boundary for the boiler or the condenser. We're going to assume that it's all the same temperature, so it's not really going to matter to us. It's pretty reasonable to imagine that, the temperature at the boundary at the boiler is basically all the same. The temperature of the boundary of the condenser is pretty much all the same. And so we're going to write this as this temperature at the boundary times the change in specific entropy is equal to Q dot over m dot.
I mean, is that like saying some of it's lower and some of it's higher?
Yeah.
So there's some temperature that you could just say effectively is
Right.
average?
I mean, all we're doing is we're saying, we could even state right at the start, like, let's just assume that this temperature is constant. Then you can pull it out of the integral, So that's kind of what we're doing. But it doesn't have to be constant. It just has to be, we just know that in whatever the range of temperatures is in there, there's some temperature in that range where this is true. That's all. It's just being kind of extra careful. But we could have just said it's constant, pull it out. Okay, so this statement now we know is true for every process in the cycle. And now we're going to use this for each one of those processes that we've defined. So first is from state 1 to state 2. That's the isentropic turbine. Well, we know that S2 is equal to S1. So delta S is 0. And so we know that, let's see, where are we going with all this? I guess really this is all we need. I'm going to just scratch that out. This all we're doing using this first stage for is to say, okay, those two entropies are the same. The second process, 2 to 3, this is the isobaric condenser. Well, we're going to start with that box statement that says Q dot over M dot is equal to this temperature delta S. In the condenser, our Q is heat leaving the system. In this, so this Q dot in this statement is, it uses the first law sign convention. At the condenser, we have heat leaving, so it has to be negative. So we're going to replace this Q dot with negative QC dot. So negative QC dot over M dot is equal to TC at the condenser. That's a specific temperature at the condenser times delta S. And so we can rewrite this as negative QC dot over M dot is equal to TC times, this is the entropy at state 3 minus the specific entropy at state 2. Then from 3 to 4, we have an isentropic pump. So again, I'm going to start with the boxed equation. We have Q dot over M dot is equal to, well, I don't even have to start there. Sorry about all the erasing. We can just say, it's isentropic. So all we're trying to get to is that the specific entropy at state 4 is equal to the specific entropy at state 3. These two isentropic parts, we're just going to use these for substitutions later on to make cancellations. That's all we're doing those for. Okay, and so then the last one from 4 to 1. That's an isobaric boiler. So again, this is heat transfer. So we'll start with the boxed equation. Q dot over M dot is equal to T times delta specific entropy. This time, the heat we're dealing with is QH because we're at the boiler. That's positive, so we don't need the negative sign here. So we can replace this with QH dot over M dot is equal to the temperature at the boiler times the change in specific entropy. And I'll rewrite this as QH dot over M dot is equal to the temperature at the boiler times the specific entropy at state 1 minus the specific entropy at state 4. Okay, so now we have all these relationships. So for each one of these, our final equation is the thing that we're going to use. And the way we're going to use it is the definition of efficiency is 1 minus QC over QH we can write this as 1 minus QC dot over QH dot because it's steady state. And we can also then write this as 1 minus QC dot over M dot divided by QH dot over M dot. And so now let's plug in for that. So the efficiency is equal to 1 minus QC over M dot. We can get from the expression from 2 to 3. Okay, it's the negative of this. So I'm going to write that as, negative TC. What did I say that is? 2 to 3? Yeah. S3 minus S2 divided by the temperature at the boiler times the quantity S1 minus S4. To get rid of that sign in the numerator, I'm just going to switch the order of those specific entropies. So this is 1 minus TC times S2 minus S3 over T boiler times S1 minus S4. Now from those two isentropic stages, we have substitutions we can make. So we know that S1 is equal to S2. and S3 is equal to S4. So I'm just going to replace this one with S1 and this one with S4. And then these cancel. And you get that the efficiency of this specific ideal, this specific internally reversible power cycle is 1 minus the temperature at the condenser over the temperature at the boiler. So the fact that we had a specific computer internally reversible power cycle in mind allowed this calculation. Okay, so I don't know, the proofs are always like, the benefit of proofs is always sort of, you always wonder if it's going to take more time and energy than the benefit you get out of it. But I just wanted to show that, the real benefit of having this mathematically, of having this thing in mind, is that we can actually go and use assumptions that we've made to calculate specific things to get results that then we can apply more generally than just our specific case. This was a case where we had a specific internally reversible power cycle in mind. We figured out this very specific fact. And then since it's internally reversible and we know that all internally reversible power cycles have the same efficiency, we can say this is the best you can do for efficiency with that condenser and boiler. Okay, so the next thing we're going to do, I'm going to stop now, but so Friday, I think this is where we'll finally be able to get into problems and stuff. I don't think I have any assignment I can give you for tonight, for the next 2 days. But we're going to represent the efficiency in terms of specific enthalpies. And we'll use that to calculate the efficiency of these power cycles at different combinations of temperatures and pressures. And then eventually we'll modify that for the superheated power cycle and for the reheated power cycle. We'll start incorporating inefficiencies into the system. I haven't mentioned yet what the working fluid is for this, like what people use for a working fluid. And almost all the time, I told you that this is used in all these specific applications, all these different types of power plants. For the most part, what they use as the working fluid is just water. Yep. So these are all steam engines. You know, I mean, I think when I started reading about this, like to me, I think like, why are we studying steam engines? Like picturing engineers shoveling coal into a train or whatever. But even still, I mean, water uh, has a pretty big latent heat, and the the latent heat is really what you're taking advantage of in this power cycle, and it's also obviously very cheap to acquire, um, and so water just works really well.
Can you think of latent heat as like the relative width of the vapor dome?
Yes, exactly.
Think of it that way?
I mean, it depends what you're. So, yeah, what it is, I guess it's how much energy it takes to go from one side of the vapor dome to the other. So that might not be like in this case, depending on what vapor dome you're looking at. Here, the width of the vapor dome is an amount of specific entropy, but it's how much energy it takes to go from one side to the other.
So in terms of energy.
Yeah, so in a T little u diagram, it's the width from one side to the other. That's correct.
So is that also a property of like refrigerants?
Yeah, what you want in a refrigerant is you want your temperature and pressure, your saturation temperature and pressure, to be at the temperature and pressure that you're working at. You know, I mean, so whether it's the compressor in a refrigerator or ambient temperature and pressure or whatever, you just don't want to spend a lot of money getting to that saturation point. And then, yes, you want it to be wide also, because the narrower that amount of energy is between a saturated liquid and a saturated vapor, the less benefit you're getting out of that constant temperature process to go from one side to the other.
So like you'd have to do more cycles to get
Right.
the same effect.
Exactly. Yep. Okay. And remember, there's a quiz on Friday. So get ready for that. Okay. Goodbye.